Welcome to the sixth lecture on the category of vector spaces, titled Quotient Vector Spaces. Let's review our previous lectures. We have introduced vector spaces as a type of algebraic structure with an addition and a scalar multiplication subject to certain properties. Morphisms between vector spaces are called linear maps. Subspaces are vector spaces obtained by restricting the operations of a vector space to certain subsets that are closed under addition and scalar multiplication. Images and pre-images of subspaces by linear maps are subspaces as well. There is a function called span on the power set of a vector space, V, which sends a subset A of V to the smallest subset of V containing A. This subspace is the set of all linear combinations of vectors in A. In this lecture, we are going to study the notion of a quotient vector space, constructed from a special kind of equivalence relation called linear equivalences. An equivalence relation on a vector space E is called linear when, for all x, y, z, and w, if x is equivalent to y and z is equivalent to w, then x plus c is equivalent to y plus w, and if for any scalar lambda and for any x and y in E, if x is equivalent to y, then lambda times x is equivalent to lambda times y. So in other words, an equivalence relation is linear when it is compatible with the operations of a vector space. Now, we have the characterization of linear equivalence relation that follows the same pattern we've seen with linear maps and subspaces. So we're just going to state the theorem. You can prove it for yourself. It's very easy. An equivalence relation on a vector space is linear if and only if for all scalar lambda and for all x, y, z, and w in your space E, x is equivalent to y and z is equivalent to w implies that lambda times x plus z is equal to lambda times y plus w. Now, the core observations for this lecture is that linear equivalences are entirely described in terms of subspaces. So let's fix V a vector space over a field K. An equivalence relation on V is linear if and only if there exists a subspace M of V such that for any two vectors x and y in V, x is equivalent to y if and only if x minus y is an element of M. Moreover, this vector space M is the equivalence class of the zero vector. So we are going to prove this very important theorem for this lecture. So let's start our proof with a linear equivalence relation on V. And let M indeed be the equivalence class of 0. I'm going to first show that M is a subspace of V. First note that since equivalence relations are reflexive, 0 is equivalent to 0, so by definition 0 is an element of M. Now let's take two vectors x and y in M, which by the way means that x is equivalent to 0 and y is equivalent to 0, and then take any scalar lambda. And let's do a simple calculation using the fact that my equivalence relation is linear. Lambda x plus y is equivalent to lambda 0 plus 0, which is 0. So that means that lambda x plus y is indeed an element of M, and thus we have shown that M is a subspace of V. Last, let's prove that our equivalence relation has the expected form. So let x and y be two vectors in V that are equivalent. Then x minus y can be calculated at x plus minus 1 times y. But then x plus minus 1 times y is equivalent to 0 using the fact that our equivalence relation is linear. So that means that x minus 1 is indeed in M by definition. And conversely, if x minus y is indeed in M, for some x and y vectors in V, then the same calculation done backward shows that x plus minus 1 times y is equivalent to 0. And again, using linearity of my equivalence relation, it means that x is equivalent to y. Okay, so if we have a linear equivalence relation on V, and we define M to be the equivalence class of 0, and first of all, M is a subspace of V, and second of all, the equivalence relation is simply given by x is equivalent to y if and only if x minus y is an element of M. So let's now prove the converse. That is, let M be an arbitrary subspace of V, and let's define a relation on V as follows. For any two vectors x and y in V, x is related to y if and only if x minus y is an element of M. And I would like to know if this relation is indeed a linear equivalence relation of V. The first thing I'm going to check is that it's actually an equivalence relation. So pick an x vector in V. Then x minus x is 0, of course, and that's an element of M, because M is a subspace. And this means by definition that x is related to x. Moreover, if x is related to y for x and y two vectors in V, then x minus y is in M, that's the definition of our relation. But then y minus x is, of course, minus 1 times x minus y, and that is an element of M, as M is a subspace. And therefore, we have shown that y is related to x. So our relation is reflexive and symmetric. Remains to show that our relation is also transitive. So we take three vectors of V, x, y, and z, with x minus y in M and y minus z in M, which means, in other words, with x related to y and y related to z. As M is a subspace, of course, we have that the sum of any two vectors of M is still a vector of M, so x minus z in particular, which is x minus y plus y minus z, is a vector of M. So x is related to z. And so we have shown that our relation is indeed an equivalence relation. Last, it remains to prove that our relation is linear. So let x, y, z, and w be vectors in V, such that x is equivalent to y and z is equivalent to w, and let lambda be some scalar. So by definition of our relation, we have that x minus y is an element of M, since x is equivalent to y, and z minus w is an element of M, since z is equivalent to w. Then we calculate lambda x plus z minus lambda y plus w, which, by reorganizing the terms, is lambda times x minus y plus z minus w. So we recognize here a linear combination of two vectors in M. Therefore, as M is a subspace, this is an element of the subspace M again, which means by definition that lambda x plus z is indeed equivalent to lambda y plus w, as we desired. This proves that we have indeed defined a linear equivalence relation. So in conclusion, this theorem tells you that equivalence relations that are linear are simply given by this very explicit expression and are parameterized by subspaces of the vector space. Now, when we have defined an equivalence relation, it is natural to look at the equivalence classes for this equivalence relation. When the equivalence relation is linear, as you would expect, the equivalence classes are going to be special. Since linear equivalence relations are entirely described by the subspace that's a class of 0, we're going to introduce a simplified notation. If M is any subspace of a vector space V, then for any two vectors x and y in V, I write x is equivalent to y modulo M to mean that x minus y is an element of M. And the linear equivalence thus defined is simply called equivalence modulo M. And we know that every linear equivalence relation is of that form. Sometimes people will even actually write x equal y modulo M with a slight abuse of notation. So equivalence classes of linear equivalence relations are actually of a very specific form, namely, if M is a subspace of a vector space V, then the equivalence class of x, vector in V, for the equivalence relation modulo M is simply the set called x plus M, which is really the set of vectors of the form x plus y, where y ranges all over M. So we take the vector space M and we translate it by x. That's the equivalence class of x. The proof is reasonably easy. So first of all, let's take an element z in x plus M in the translate of M by x. What it means is that z equals x plus y for some y in M. So if you calculate x minus z, well, you get y, and that's an element of M. Therefore, it means that z is equivalent to x modulo M. So z is in the equivalence class of x. Conversely, if z is in the equivalence class of x, that is z is equivalent to x modulo m, then set y to be z minus x. By definition of our recurrence relation, it means that y is an element of m. Thus, z equals x plus y, and therefore z is an element of the translate of m by x. This concludes our proof that the equivalence class of x for the recurrence relation modulo m is indeed the translate of m by x. So that's it. We have a complete description of equivalence classes for every vector for a linear equivalence relation, and there is a name for sets that are translate of vector spaces. They are called affine spaces. So we have introduced the notion of linear equivalences, which are equivalence relations compatible with the algebraic structure of a vector space. We've characterized linear equivalences as being simply equivalence modulo a subspace. And we've seen that equivalence classes of a vector for linear equivalence are affine spaces or translate of subspaces. And so now we have all the necessary ingredients really to understand what quotient vector spaces are. If you give me any equivalence relation on a set, there is an associated set called a quotient set, which is a set of all equivalence classes. Here we start from a vector space as a nice type of equivalence, namely linear equivalence. So we hope that the quotient set of a vector space by linear equivalence is itself a vector space. I begin with the standard notation. If M is a subspace of a vector space V, then the quotient of V by M, denoted by V quotient M, is a quotient set of V by the linear equivalence of equivalence modulo M. So indeed our theorem states, if M is a subspace of a vector space V over a field K, and if pi is the canonical surjection from V onto V quotient M, then V quotient M is a vector space over the same field K for the following two binary operations. If I take any two x and y in V, then I define the sum of the equivalence class of x and the equivalence class of y as the equivalence class of x plus y. And for all scalar lambda and x in V, I define the product lambda times the equivalence class of x as the equivalence class of lambda times x. So if you look at this definition, it almost looks like I'm stating that pi is linear, and in fact I am, but the process goes a little bit differently. What I'm doing here is I'm defining an addition and a scalar multiplication of the quotient in such a way that indeed the canonical surjection becomes linear. The problem with these definitions as they are stated is we don't even know if they make sense, because if you give me two classes in V quotient M, let's call them A and B, then A is the equivalence class of some x, B is the equivalence class of some y, and therefore what this definition here says is that A plus B should be the equivalence class of x plus y, but the problem is that in general A is also the equivalence class of some z, and B is also the equivalence class of some w, and now I'm saying that A plus B is also the equivalence class of z plus w. So the question is, are these two definitions, these two possible choices of a possible sum for the equivalence class of A and B, are they the same? Are they compatible? And of course we are going to prove that indeed it is the case, so that we have indeed our structure of vector space. So let's do that and let's prove our theorem. So we're going to start the proof of our theorem by indeed checking these operations are well defined. To that end, let x, y, z, and w be vectors in V, such that x and z are equal modulo m, and y and w are equal modulo m. And the idea here is that I want to check that the equivalence class of x plus y is equal to the equivalence of class of z plus w, so that my addition is well defined. So since x is equal to z modulo m, it means x minus z is an element of m, and similarly y minus w is an element of m. And then I'm going to compare x plus y with z plus w. I take their difference, but you can rearrange the terms by associativity and commutativity to observe that you really have the difference of x minus z, which is an element of m, and y minus w, which is an element of m. M is a subspace, so this difference is indeed an element of M. What it means is that x plus y is equal to z plus w modulo M. In other words, they have the same equivalence class. So the addition is well defined. It does not depend on the choice of representative for your equivalence class. The same holds for the scalar multiplication, so I'm not going to write it, it's the same idea. So next I need to check that my quotient set with these two operations is indeed a vector space, and it's not a subspace of anything. I mean, it's just this quotient set, so it's a subset of the power set of V, but there's no linear structure on that power set. So we have to go back to the original definition of what a vector space is here. But the key observation is that this map pi, the canonical surjection, is indeed surjective, and it intertwines the addition and scalar multiplication of V with, respectively, the addition and scalar multiplication on the quotient. So, because of this simple property, all the properties of V are going to be transported to the quotient. So let's see what I mean formally. Let's check that this new addition on the quotient is associative. So I take three elements in the quotient, let's call them A, B, and C. Since pi is surjective, there exists x, y, and z in V, such that pi of x equals to A, pi of y is equal to B, and pi of z equals to C. All right. And when we calculate A plus B, between parentheses, plus C, okay? So, well, we replace A, B, and C by their expression in terms of pi, no problem there. But then, if you write what this means, just looking at the definition of addition, it means that I'm calculating the equivalence class of the sum of x plus y, the sum of x and y, with z. Okay, with this grouping here. But now, what it means is that we're calculating the equivalence class of a vector in V, and this vector in V is written as a sum, and we know the sum in V is associative, so we can move the parentheses. This tells me that really I can then use the definition again of my addition of equivalence class to see that pi of x plus the sum of y and z is the same as pi of x plus the pi of the sum of y and z, which in turn I can rewrite as pi of y plus pi of z. And I recognize this is indeed A plus the sum of B and C. So I've proven associativity, and all I did is use associativity of V. And every property that I need for the quotient set to be indeed a vector space will be proven the same way. So I'll give you a few more examples, but we just to see what's going to happen. We're not going to do them all. So for instance, since we want to prove that the quotient space is in particular a group for the addition, I need a neutral element. Well, the neutral element is, of course, pi of 0. And that's easy to check. I mean, if you you look at the definition of there and you add 0, pi of x plus pi of 0 is pi of x plus 0, which is pi of x. So that's reasonably obvious. And we have an inverse. The way you take an inverse is if you take an element A in the quotient, then it's pi of x for some x. Then you take this x in your vector space V. It has an opposite in V for the addition, minus x. And then I take the class of minus x. And if I add it up to A, I get the class of 0. And this is fine because, again, we know that whatever vectors I would take in the class of minus x, I would get the same result because we've already shown that our addition is well defined. So we have an opposite for any class in V quotient M. Similarly, we would have the addition is commutative. It's the same trick. So I'm going to skip that. I just want to give one example involving the scalar multiplication just to see what goes there. But it's the same trick. So I'm going to prove the distributivity properties. So if I take two elements of the quotient, call them A and B, and lambda some scalar, then again, because pi is surjective, A is pi of x and B is pi of y, for x and y two vectors in V, then it just means that A is the equivalence class of x and B is the equivalence class of y. And then if I calculate lambda times A plus B, just looking at the definition up there, it's pi of lambda times the sum of x and y, but then I know that the external multiplication or scalar multiplication is distributive with respect to the vector addition, so lambda times the sum of x and y is the sum of lambda x and lambda y, and then you recognize right there that by definition this is the sum of lambda times A and lambda times B. And all the properties follow in the same manner. So there are, of course, a few more properties to check, the compatibility relations, but they follow exactly in the same way as these proofs. They all follow from the fact that A, pi is surjective, and B, pi intertwine the operations on V with the operation on the quotient. And from there, everything follows. So we have indeed proven that quotient's sets of vector spaces by linear relations are vector spaces in a very natural way. And the way to remember all that is basically to remember that the canonical surjection is linear for the operations on the quotient. Now, there is a little observation here that I make because I think it's kind of interesting a little bit. If you look at what we've done, you give me any subspace of V, and I make a quotient, and that quotient becomes a vector space, and I have a natural linear map from V to that quotient, namely the canonical surjection. And then you could look at what's the kernel of this canonical surjection. It's a linear map, so if you look at all the vectors of V that are mapped to the 0 element in the quotient, well, we know what they are. They're all the elements that are equivalent to 0. They are the equivalence class of 0, which is that subspace M that I've chosen to define my equivalence relation. So that means that any subspace of a vector space is actually the kernel of some linear map. Now, this linear map has to be on the whole set, okay? I mean, if you give me a vector space, I can always define the map that to every vector map to 0, and voila, we have a map whose kernel is a whole space. We haven't done anything interesting here. But that's a little different here. It's a little different because I give you a subspace of a fixed vector space V, and I want a map on all of V, whose kernel is exactly that subspace you gave me. So the map has to be defined on all of V. Sure, I know it's 0 on the subspace you want it to be 0 on, but what am I supposed to do with the rest, right? Well, here the answer is use a quotient vector space. With a quotient vector space structure, the map that's going to work is a canonical surjection. So you take M in your subspace, you quotient V by M, take the canonical surjection, it's a linear map whose kernel is exactly M. So every subspace of V is a kernel of a map that is linear on all of V. Now, to conclude this lecture, well, when we talk about equivalence relations, the important observation is that there is a factorization theorem for functions. But here, again, we are in the realm of vector spaces, in the category of vector spaces. So I specifically want to work with linear maps and see if they factor through the quotient in a natural sense. So to do so and to state my theorem nicely, I'm going to review a theorem which says that if V and W are two vector spaces over a field and I have a linear bijection from V to W, then the inverse map, phi inverse, is also linear. This is to kind of get rid of any ambiguity about the notion of an isomorphism. Okay, so the proof is fairly standard because it is a phenomenon that occurs with any algebraic structure, that essentially an isomorphism is a bijective map that's a morphism. It's not true, however, in general category theory. For instance, in the category of topological spaces, there are continuous bijective maps whose inverse map is not continuous. But in the case of algebraic structure, this is standard, and the proof I'm going to make is an archetype of these kind of proofs. So if x and y are two vectors in W, then there exist two elements A and B in V, so that phi of A is x and phi of B is y. Well, yeah, because phi is surjective, in particular, as a bijection. And if I take any scalar lambda, then I can calculate phi inverse applied to lambda x plus y. Alright, well, it's phi inverse of lambda phi of A plus phi of B, and that comes from the definition of A and B. I just replace x and y by their expressions in terms of phi. But now phi is linear. So lambda phi of A plus phi of B, that's phi of lambda A plus B. And this is good because now you see we're calculating phi inverse of phi of something. Phi is an actual bijection, these things cancelled, and we're left with phi inverse of lambda x plus y is lambda A plus B. Now what is A? Well, phi of A is x, so A is phi inverse of x. And same with B, B is phi inverse of y, so you replace, and you get the expression that you desired. That is, the phi inverse applied to lambda x plus y is lambda phi inverse of x plus phi inverse of y. You see that phi is indeed a linear map. So we can now introduce the notion of a linear isomorphism as just being a linear bijection. The term isomorphism comes from category theory, where properly defined, if you have a morphism from an object V to an object W, it is an isomorphism if there is another morphism from W to V, such that when you compose them one way, you get the identity of V, and you can compose them the other way, you get the identity of W. In our case here, what happens is we have, if we have a linear bijection, is that we automatically have indeed that the inverse is also a morphism, that is, it is automatically linear, so our definition here is compatible with the general usage in category theory. So we can conclude with a factorization theorem for linear maps. So if V and W are two vector spaces over K, and if phi is a linear map from V to W, then there exists a linear isomorphism, psi, from the quotient of V by the kernel of phi onto the range of phi, such that for any vector x in V, phi of x is psi of the equivalence class of x. So the proof goes as follows. Take any two vectors x and y in V, and suppose that the difference of x and y is in the kernel of phi. In other words, suppose that x is equal to y modulo the kernel of phi. And if I calculate phi of x, it's the same thing as by linearity calculating phi of x minus y plus phi of y, but then phi of x minus y is 0. So that's just phi of y. Now there is a standard factorization theorem that can be applied here from the general notion of recurrence relation and quotient set, which gives me the existence of a unique map, psi, from V quotient the kernel of phi to W, such that phi is equal to psi composed with this canonical surjection. So that's general set theoretic, and it simply follows from the fact that phi is constant on the equivalence classes of the modulo kernel of phi relation. In other words, it is constant on the cosets of my relation modulo kernel of phi. And the whole point here is that our linear equivalence is defined using the kernel of phi. So now this map psi right now is just a function from the set V to the quotient set V, quotient kernel of phi, but I want to prove that psi is actually linear. And it is linear because phi is linear and the canonical surjection pi here is linear as well. Let's prove that. Let A and B be two elements of the quotient V quotient by kernel of phi. Then, by definition of the quotient space, there exists x and y in V, so that A is the equivalence class of x and B is the equivalence class of y. In other words, A equals pi of x and B equals pi of y. If I take any scalar lambda and I compute lambda A plus B, it equals to, by definition of the operation on the quotient, pi of, or the equivalence class of, lambda x plus y. So, let's calculate psi of lambda A plus B. Well, by definition, it's psi of pi of lambda times of x plus pi of y, but using the operation of my vector space, it ends up being psi of pi of lambda x plus y. In other words, I use the linearity of pi. But then, by definition, at a set theoretic level, psi composed with pi is phi. So we have that psi of pi of lambda x plus y is simply phi of lambda x plus y, and phi is linear. So I can calculate that. That's lambda phi of x plus phi of y. But again, because of the relation between psi and psi coming from set theory, that equals to lambda psi of A plus psi of B. So you've proven that psi is linear. All that's left is to prove that it's actually a linear isomorphism between the stated spaces. So, well, that means that since I know psi is linear, I need to prove that it's bijective, then I will know automatically it's an isomorphism. In our case, it's by definition even, but even in the categorical sense, that would apply. So I'm going to prove that psi is injective first. So let's assume that psi of A is 0. And then where A is an element of the quotient, therefore it's of the form equivalence class of some x in V. Then if psi of A is 0, and A is pi of x, the equivalence class of x, then by the relation between phi and psi, it means phi of x must be 0. And that means in turn that x is the kernel of phi. The kernel of phi is exactly what becomes the 0 element of the quotient space. So A is the equivalence class of 0. In other words, it is when I write A equals 0, but inside the quotient space, V quotient by kernel of phi. So psi is injective. And, well, if you just look at the definition, it's trivial that the range of phi is a range of psi because the map pi, the canonical surjection, is indeed surjective. And so we indeed have a bijection as a function, just a regular function, from the quotient space, V quotient by kernel of phi, to the range of phi. But that function is also linear, so it is a linear isomorphism as claimed. So this concludes our discussion on quotient vector spaces. They are very useful objects. They will actually play a role in our work on dimension theory and other applications as well, of course. They are actually quite common in reality, so it's a notion well worth getting familiarized with. We are going to now start dimension theory on vector spaces, and the first step to that, toward defining dimension and studying the properties of finite dimensional vector spaces, is to discuss linear independence. It's related to the notion of finding a minimal set that spans a given vector space. This will be the topic of lecture 7, called linear independence.